All right, we're ready to go. Thank you for your patience.
All right, so this allows me to wander around a little more. All right, so I'm going to talk to you about something completely different. This is a talk about basically the results of the Pheonix mission and what we learned about the habitability of the Pheonix landing site. This is actually now out in print. See this paper here in the Journal of Geophysical Research. It's available online. I think the actual print version is still hasn't come out yet. Okay, so first of all, I'm going to present a formalism. This is going to be a little heavy on the technical end talk, so I'm going to present a formalism for determining the probability of habitability, or a habitability index, which is a way of understanding in a more quantitative way what does it mean for a place on Mars to be habitable for life. Then I'm going to review, first I'm going to review the Pheonix payload and mission results. Then I'm going to describe how the mission results were used to estimate the factors that make up this habitability index. And then I'm going to show the resulting habitability index for Pheonix and other sites visited on Mars. And then finally, discuss implications for future missions that result from that analysis. So a key objective of the Pheonix mission was to search for a habitable environment. What does that mean? So first of all, apply this definition. A habitable environment is one that is capable of supporting living organisms with capabilities similar to terrestrial microbes. Now there might be other definitions, but this is the one we're applying because it's the only one we know anything about. These conditions might be found in the present, the recent past, or the distant past. There is a group called MEPAG. This stands for the Mars Exploration Payload Analysis Group. It's kind of a funky name, but what it really is it's the community that is the Mars science community. And by consensus, this community meets and they decide what the objectives of the Mars program are, and they write them down and they create this document. It's a living document. It's called the roadmap. And as we learn new things about Mars, the document changes, but it has, for decades, for about a decade, had the overarching goal of searching for life on Mars. So that's the overarching goal of the Mars program, is to search for life. So they have now defined a strategy, which is how do you do that? And that strategy is written down in an archival roadmap document. And it says that you will first find environments that are or were habitable, and that having found such an environment, the next step would then be to search for evidence of life consistent with what that environment would support. And that, furthermore, a life detection mission would be warranted only if the probability of a habitable environment is greater than 50%. So they have defined that there is a way to actually make a number for the probability of this habitable environment, but they didn't go on to actually show how you would do that. So I show a way to do that. And this is inspired by the Drake equation, which is, the Drake equation was originally put forward by Frank Drake in the thing that started the search for extraterrestrial intelligence. So it is a way of defining the probability of life in the universe. So drawing from that inspiration, I've developed this way of evaluating habitability. So basically what you have is, again, MEPAG identified 3 factors that control the potential for habitability. These were the probability that liquid water has been present, the probability of a biologically available energy source, and the probability that the chemical building blocks of life are present. So these factors have to be present simultaneously. So MEPAG again suggested the defining habitability index, which is the product of these probabilities. So that's it, the product of the 3. I looked at this and decided that it was necessary but not sufficient. It was not complete. So I've included an an additional factor. The probability of the environment is benign or non-toxic. So in other words, all these things could be true, but there could be something that kills you in the environment, and it still would not be habitable. So I've added this. The environment is actually benign. Okay, so each of these 4 probabilities then are evaluated by decomposing them into contributing factors and then using the observations to evaluate each of the factors. And then the probability is computed as a normalized sum of the factors, which are then weighted to each other by the importance of the factors. So basically, using standard probability theory and probability definitions, you can actually do an evaluation of this by evaluating each one of the factors independently. So that's what I have done, and I'm going to show you how the Pheonix results go into assigning values to these factors. However, there are some problems with this. First of all, none of these things really have an absolute value. So there's really no way to assign an absolute value. All you can do is estimate the likelihood of anything being true from the observations. Secondly, Pheonix did not really get all the measurements you would need to evaluate all the factors. Pheonix was a reflight of some instrumentation that was originally designed for a different mission, the Mars Polar Lander mission, which was a mission that failed on landing. And so Pheonix had heritage instruments, so it didn't actually ab initio say, we're going to go look for habitable environment and we're going to select our instrumentation, specifically targeted to that. It was more that after we had the instrumentation, we thought, what can we do usefully with this instrumentation? And this is what we came up with. Finally, things we did measure often have more than one interpretation. This is often a problem in science. So given that that's the case, we'll muscle on and do the best job we can. So conventions that are used to assign values to the factors, each factor is assigned a value from 0 to 1 corresponding to null to high. And where high means you actually measured it and the evidence is strong, and the corresponding value is 1. Medium high means you measured it and the evidence is strong, or there's strong theoretical arguments and the value is 0.75. Medium means it was measured but there's alternative interpretations, or the measurement is uncertain, or you didn't measure it but there's strong arguments for a particular answer, and the value 0.5 is assigned. Low means it was measured, but there's lots of possible interpretations, or the measurement is uncertain, or it wasn't measured, but there are weak arguments that the factor should be present. And again, an even lower value, 0.25. And null means you looked for it, but it was not observed, or it was not measured, and there's no good argument that it should be there. So this is more like you really think it's not there. That's when you give it a 0. Okay, so here's the Pheonix payload, which is used to assess the habitability. And here is a kind of an artist's concept of the lander sitting on the surface of Mars. It has a camera system, the surface stereo imager, a MECA package which did wet chemistry, optical microscopy, and atomic force microscopy. It had an organic analyzer. This is the thermal evolved gas analyzer package. It had a robotic arm, also with a camera on the robotic arm. And it had a meteorology package with an upward-looking LiDAR. I'm going to go through each one of those in a little more detail. This is the camera system. The surface stereo imager was built at the University of Arizona. It provides stereo images from which you can make digital elevation models. It's also multispectral. It has a suite of filters that allows you to get geologic and mineralogic information and atmospheric dust and cloud properties by looking upwards. They're through a solar filter. Here's the robotic arm, which to some extent allows the sampling of icy soils. The arm itself is a digging arm. It was really originally designed to scoop soil. It was not good for accessing ice. There was a little tiny drill, it's about 2 centimeters long, added to the back of the arm to allow you to actually get through hard cemented material, icy material. When that material was drilled, the drill cuttings were actually moved up into the back of the scoop so that you got the drill cuttings directly into the scoop by that method. This thing sticking out of the side of the arm is something called the thermal and electrical conductivity probe, and it allowed you to stick these needles into the soil, directly into the soil, and measure if there was any liquid water seen in the soil by measuring the conductivity of the soil. It also, when in the atmosphere, could be used for getting you atmospheric relative humidity. And it looks like I have animated things. This is the robotic arm camera, which looks at the material in the scoop. Okay, the next element of the payload is this thermal and novel gas analyzer. This is an instrument that basically takes soil that's deposited in little ovens. So each one of these things is a door. And that's actually sitting at about the angle that the door is. It's about a 45-degree angle. So you plop soil down, the door is opened, plop soil down into the instrument, and the soil goes inside the instrument, and it is slowly heated to 1,000 degrees centigrade. Then by measuring the calorimetry, which is the amount of heat it takes, or the amount of energy it takes to get the sample to heat up by a certain amount, you can then track phase transitions and identify specific minerals, because minerals decompose at different temperatures. Then as things decompose, they give off volatiles, and the volatiles are measured with a mass spectrometer. So by doing that, you can measure the presence of water and other volatiles. So in particular, organic compounds would decompose into volatile organic gases that are measured by the mass spectrometer. It also allows certain minerals, such as carbonates, to decompose at known temperatures, so you can see carbonate minerals. And using a mass spec, you can determine isotopic ratios of key elements. So that was kind of our flagship instrument, was the TIGA instrument. Another instrument that was flown was the wet chemistry lab. And what happens here is, here's an inlet port, and you drop soil on that input port, goes inside the instrument, and then mechanisms inside the instrument add water to the soil, and using ion selective electrodes, you then determine quantities of soluble ions, such as ions of sodium, potassium, calcium, nitrogen, chlorine, magnesium, and sulfate. It also measures the pH of the sample and the electrochemical conductivity of the sample. Part of the MECA payload was the microscopy station, and this is basically an optical microscope illuminated by LEDs, red, green, blue, and ultraviolet LEDs, and samples went in to a sample wheel and sat on a substrate in the sample wheel. The resolution of this optical microscope was really very good. It's a factor of 10 better than the optical microscope on the Mars Exploration Rover, 3 microns per pixel. Plus, this atomic force microscope has scanning electron microscope type resolution, like 10 nanometer topography of soil grains. Furthermore,